In this video lecture, we are going to study about the line broadening mechanism, under which we will study about the homogeneous broadening and inhomogeneous broadening. In the inhomogeneous broadening, we will study about the natural broadening, collision broadening, and inhomogeneous broadening, we will learn about the Doppler broadening. Myself, Virendra Kumar, professor and scientist. So let's start the video lecture. Friends, because this video is going to be very interesting and informative, so please remain throughout the video lecture. And if you have not subscribed the Sai Academy channel, please subscribe the Sai Academy channel, and please don't forget to press the like button and share the video with your friends and colleagues so that they can also learn about this video. As you know, the radiation coming out of a collection of atoms making transitions between two energy levels E1 and E2 is never perfectly monochromatic. So we will discuss in this video lecture some important line broadening mechanism and obtain the corresponding line shape function, since this determines the operation characteristic of the laser, such as the threshold population inversion and the number of oscillating modes. The various broadening mechanisms can be broadly classified as homogeneous or inhomogeneous broadening. In case of homogeneous broadening, like natural or collision broadening, the mechanism act to broaden the resonance of each atom in identical fashion for whole of the system, and it is because of the interaction of the atom with the phonons of a crystal lattice in the solid state material. And in case of homogeneous broadening, the probability of absorption or emission of radiation of a certain frequency is the same for all atoms in the collection. Thus, there is nothing which distinguishes one group of atoms from another in the collection of atoms. In case of inhomogeneous broadening, different groups of atoms are distinguished by different frequency responses. For example, in Doppler broadening, group of atoms having different velocity components are distinguishable and they have different spectral responses. Similarly, broadening caused by local inhomogeneities of a crystal lattice acts to shift the central frequency of the response of individual atoms by different amounts, thereby leading to inhomogeneous broadening. Before proceeding further, let us understand about the Lorentzian line shape function and the Gaussian line shape function, because we are going to use these line shape functions in the case of line broadening mechanism. So Lorentzian line shape function, it is given by L is equal to 1 by 1 plus x square, where L signifies a Lorentzian function standardized for spectroscopic purposes to a maximum value of 1, and x is a subsidiary variable defined as x is equal to p minus p naught divided by omega by 2, where p naught is the position of the maximum corresponding to transition energy E, and P is a position and omega is the full width at half maximum. The FWHM is the width of the curve when the intensity is half the maximum intensity. So you can see here that when the intensity is half, we are talking about this width. So this is the width of the curve when the intensity is half of the maximum intensity. This occurs at the point P is equal to P naught plus omega by 2 on both sides. The unit of P naught, P and omega are typically wave number or frequency. The variable x is dimensionless and is 0 at p is equal to p naught. Now, in the case of Gaussian line shape function, Gaussian line shape has a standardized form given by g is equal to e to the power minus log 2 x square. The substitutive variable x is defined in the same way as for a Lorentzian shape. So both this function and the Lorentzian will have a maximum value of 1 at x is equal to 0 and a value of 1 by 2 at x is equal to plus minus 1. Now we will discuss natural broadening in detail. We already know that an excited atom can emit its energy in the form of spontaneous emission. In order to investigate the spectral distribution of this spontaneous radiation, we will write the rate of decrease of the number of atoms in level 2 due to transition from level 2 to level 1 as dN2 by dt is equal to minus a to 1 n2. For every transition and energy h cross omega naught is equal to E2 minus E1 is released. So this much energy is released for every transition. Thus the energy emitted per unit time per unit volume will be given by Wt is equal to modulus dN2 by dt into the energy released per transitions, that is h cross omega naught, that is equal to modulus minus a to 1 n to h cross omega naught, and this is equal to a to 1 n to h cross omega naught. Now substituting the value for n2, we get a to 1 n to 0 into e to the power minus a to 1 t into h cross omega naught, that is n to 0 a to 1 h cross omega naught e to the power minus a to 1 into t. So this is the energy released per unit time per unit volume for the transition of the atoms from level 2 to level 1. Now, since this equation describes the variation of the intensity of the spontaneously emitted radiation, we may write the electric field associated with the spontaneous radiation as Wt is directly proportional to the square of the amplitude of the electric field. That is, in terms of decreasing amplitude, the electric field associated with the spontaneous radiation as it is equal to E naught e to the power I omega naught t e to the power minus t by 2 tsp, where tsp the spontaneous lifetime, and if we square of this, then it will give the energy variation or intensity of the spontaneously emitted radiation, as this is proportional to Et square, where Tsp, as I told, is the spontaneous lifetime, and that is written in terms of Einstein spontaneous coefficient. So we are using the fact that intensity is proportional to the square of the electric field. Thus, the electric field associated with spontaneous emission decreases exponentially. Now, in order to calculate the spectrum associated with the wave described by this, equation, we will use the Fourier transform as e omega is equal to 0 to infinity e t e to the power minus I omega t dt. Substituting the values of et, we get 0 to infinity e naught e to the power I omega naught t e to the power minus I omega t into e to the power minus t by 2t sp dt, which after simplification gives e naught 0 to infinity exponential of I omega naught minus omega t minus t by 2t sp dt, which is equivalent to e naught into 1 by 1 by 2 t sp plus I omega minus omega naught. We have this equation where t is equal to 0 is the time at which the atom starts emitting radiation. Since intensity is directly proportional to the square of this Fourier transform, that is intensity I omega is directly proportional to the E omega whole square. Hence the line shape function can be given as for spontaneously emitted radiation as g omega is equal to k into 1 by omega minus omega naught whole square plus 1 by 2 tsp whole square, where k is a constant of proportionality which is determined by the normalization condition of g omega d omega is equal to 1. Therefore, we have to find the k. So, substituting this value of g omega, we get k d omega divided by omega minus omega naught whole square plus 1 by 2 tsp whole square is equal to 1. Therefore, 4 tsp square into k integration d omega divided by 4 tsp square into omega minus omega naught whole square plus 1 is equal to 1. Now put 2 tsp omega minus omega naught is equal to p. Therefore, 2 tsp after differential gives dp, implies that d omega is equal to dp by 2 tsp. So substituting these values, we get 4t sp square k by 2t sp integration minus infinity to, so the integration is here minus infinity to infinity dp by 1 plus p square is equal to 1. After integration, this gives 2 tsp into k into tan inverse p minus infinity to infinity is equal to 1. We, after solving 2 tsp k tan inverse tan inverse infinity minus tan inverse minus infinity is equal to 1 implies that 2tsp k pi by 2 minus pi by 2 is equal to 1. After solving this, we get 2tsp k into pi by 2 plus pi by 2 is equal to 1 implies that k is equal to 1 by 2 pi tsp. So this is the value of proportionality constant. Therefore, the normalized line shape function can be given by g omega is equal to 1 by 2 pi tsp into 1 by omega minus omega naught whole square plus 1 by 2 tsp whole square. Therefore, we have g omega is equal to 2 tsp divided by pi into 1 by 4 omega minus omega naught whole square tsp square plus 1. This is a form of line shape function and is of the type of Lorentzian line shape function as we discussed earlier before starting this lecture. So this is very important relationship we just derived. So remember this relation. Now we will find the half width at half maximum. This is a type of Lorentzian line shape function. So since this represents the intensity of the spectral radiation, so the full width at half maximum of this Lorentzian is found as 1 by 4 omega minus omega naught whole square tsp square plus 1 is equal to half. This implies that for delta omega whole square tsp square is equal to 2 minus 1, that is 1. Delta omega square is equal to 1 by 4 tsp square. Delta omega plus minus can be given by 1 by 2 tsp. This is the value of frequency at half intensity. That is this. This will give the full width at half maximum. Thus, full width at half maximum is equal to 1 by 2 tsp plus 1 by 2 tsp is equal to 1 by tsp, that is equal to delta omega plus delta omega minus is equal to delta omega. That means full width. You can understand this diagram. Therefore, we have g omega is equal to 2 tsp by pi into 1 by 4 omega minus omega naught whole square tsp square plus 1. After substituting the value of TSP, we get 2 by pi delta omega into 1 by 4 omega minus omega naught square 1 by delta omega whole square plus 1. This gives 2 by pi delta omega 1 by omega minus omega naught divided by delta omega by 2 whole square plus 1. So this is the expression for the line shape function associated with the spontaneous emission in case of level 2 transition. From the diagram you can see that G omega gives maximum 2 by pi delta omega and at full width half maximum the value for the half width is 1 by 2 tsp and therefore full width is 1 by tsp that is equal to delta omega. Now we'll discuss about the collision broadening under the homogeneous broadening of the laser system. So in collision broadening what happens? In a gas, random collisions occur between the atoms. In such a collision process, the energy levels of the atom change when the atoms are very close due to their mutual interaction. Let us consider an atom which is emitting radiation and which collides with another atom. When the colliding atoms are far apart from each other, their energy levels are unperturbed and the radiation emitted in this case is purely sinusoidal, provided we neglect the decay in the amplitude due to the spontaneous emission. As the atoms come close together, their energy levels get perturbed and thus the frequency of the emission changes during the collision time. After the collision, the emission frequency returns to its original value. So, if tau c represents the time between collision and delta tau c the collision time. So tau c is the time between collisions and delta tau c is the collision time. What is the meaning of this? The tau c time between collisions, that means the time required to get near to each other by the atoms, and delta tau c is the collision time. This is the time in which the atoms get interact with each other near the interatomic distances. Delta tau c can be given by interatomic distance divided by average thermal velocity, and that if you calculate interatomic distance 1 angstrom and average thermal velocity 500 meter per second, then this value comes out nearly equal to 2 into 10 to the power minus 13 second. Now the time between collision tau c can be written as mean free path lambda divided by the average thermal velocity, and that is equal to 5 into 10 to the power minus 4 divided by 500 meter per second, and that comes out nearly equal to 10 to the power minus 6 second. Thus we see that collision time is very less in compared to the time between collisions. That means the collision is almost instantaneous. Since the collision time delta Tc is random, the phase of the wave after the collision is arbitrary with respect to the phase before the collision. So you can see here that The phase gets changed after each collision. Thus, each collision may be assumed to lead to random phase changes, as you can see in this diagram. It is no longer monochromatic, and this broadening hence is referred to as the collision broadening. Now our aim is to calculate the line shape function in case of the collision broadening to study the radiation spectra of the atom during the transition from the level 2 to level 1. The electric field associated with the wave during the collision broadening is given by Et is equal to E0 e to the power I omega t plus I phi, where phi is the phase that remains constant, is a phase and remains constant for the time t naught and t naught plus tau c. So tau c is the time between collisions. So this phase remains constant before the actual collision, but after the collision the phase changes. Each collision the phase phi changes randomly. Since the wave is sinusoidal between two collisions, the spectrum of such a wave will be given by the Fourier transformation E omega is equal to 1 by 2 pi t is equal to 0, t at t is equal to 0 plus tau c E0 e to the power I omega naught t plus phi into e to the power minus omega t dt. Which so let us solve this integration. This gives E naught by 2 pi exponential I minus omega naught t plus I phi divided by I omega naught minus omega from t is equal to t naught to t naught plus tau c. Now after simplification we get E omega is equal to E naught by 2 pi exponential I omega naught minus omega tau naught plus tau c plus I phi minus exponential I omega naught minus omega tau naught plus I phi into 1 by I omega naught minus omega, which gives E naught by 2 pi I 1 by omega naught minus omega exponential I omega naught minus omega t naught plus I phi into exponential I omega naught minus omega tau c minus 1, which is equal to E naught by 2 pi exponential I omega naught minus omega t naught plus I phi into e to the power omega naught minus omega tau c minus 1 divided by I omega naught minus omega. So ultimately we have this equation for the spectra. The power spectrum of such a wave will be given by I intensity I omega directly proportional to modulus square E omega, and that is equal to so now our aim is to calculate this quantity. So let's evaluate this quantity where E omega is equal to E naught by 2 pi exponential I omega naught minus omega t plus I into e to the power I omega naught minus omega tau c minus 1 divided by I omega naught minus omega. After substituting this value in this equation, we have equal to E naught by 2 pi exponential I omega naught minus omega t plus I phi e to the power I omega naught minus omega tau c minus 1 divided by I omega naught minus omega into, now we'll put the values of complex conjugate of this, that is e to the power exponential e naught by 2 pi into exponential minus I omega naught minus omega t minus I phi into e to the power minus omega naught minus omega tau c minus 1 divided by minus I omega naught minus omega. So after simplification, this gives E naught square divided by 4 pi square into 1 by 1 omega naught minus omega whole square into e to the power I omega naught minus omega tau c minus 1 into e to the power minus I omega naught minus omega into tau c minus 1, which further reduces to E naught square by 4 pi square 1 by omega naught minus omega square into minus e to the power I omega naught minus omega tau c plus e to the power minus I omega naught minus omega tau c plus 2 is equal to E naught square by 4 pi square 1 by omega naught minus omega whole square 2 minus 2 cos of omega naught minus omega tau c, that is equal to E naught square by 4 pi square 1 by omega naught minus omega whole square into 2 into 2 sine square omega naught minus omega tau c by 2, that is equal to E naught square by 4 pi square 1 by omega naught minus omega whole square sin square omega minus omega naught tau c by 2. So this 4 cancel with this 4. So we have now E omega whole square is equal to E square E naught square by pi square 1 by omega naught minus omega whole square sin square of omega minus omega naught tau c by 2. Therefore, we have I omega, the power spectrum of wave direct proportional to E omega square, that is equal to E naught square by pi square 1 by omega naught minus. Now, at any instant, the radiation coming out of the atomic collection would be from atoms with different values of tau c. In order to obtain the power spectrum, we must multiply this I omega by the probability P at tau c into d tau c that the atom suffers a collision in time interval between tau c and tau c plus d tau c and integrate over tau c from 0 to infinity by kinetic theory of gases. We know that probability that atom suffers a collision in the time interval between tau c and d tau c plus tau c and tau c plus d tau c is given by p tau c d tau c is equal to 1 by tau naught into e to the power minus tau c by tau naught d tau c. So this is the established fact, and we will use this with condition 0 to infinity p tau c d tau c is equal to 1 and tau c p tau c into d tau c is equal to tau naught. So these are the important thing which we utilize. Here T naught is the mean time between two collisions. Hence, the line shape function for the power spectrum can be, in the case of collision broadening, can be written as g omega, that is proportional to 0 to infinity. As I said, should be multiplied, I multiplied with p tau c d tau c, and that gives equal to a e naught square by pi square 0 to infinity d tau c by omega minus omega naught whole square sin square omega minus omega naught tau c by 2 into e to the power minus tau c by tau naught by tau naught. Here a is the normalization constant, and we will get its value by the normalization condition. So let us put omega minus omega naught is equal to alpha 1 by tau naught is equal to beta. Therefore, the equation for g omega reduces to a e naught square by pi square 0 to infinity sine square alpha tau c by 2 divided by alpha square beta e to the power minus beta tau c tau c that is equal to a e naught square by pi square beta by alpha square after into minus 0 to infinity e to the power minus b tau c cos of alpha t tau c divided by 2 d tau plus 1 by 2 integration 0 to infinity e to the power minus beta tau c d tau c. That gives a e square e naught square beta by 2 pi square alpha square minus 0 to infinity e to the power minus beta tau c cos of alpha tau c plus 0 to infinity e to the power minus beta tau c d tau c. That is equal to a into capital A into minus 0 to infinity e to the power minus beta tau c e to the power I alpha tau c plus e to the power minus I alpha tau c by 2 d tau c plus minus 1 by beta into e to the power minus beta tau c 0 to infinity. After solving this, we get g omega is equal to a plus 1 by 2 0 to infinity e power minus beta I alpha tau c e to the power minus beta minus I alpha tau c. Tau c. Here we have a is equal to t square by square alpha square for simplicity. Thus, g omega is equal to a into capital A into 1 minus 1 by 2 e to the power minus beta plus I alpha into tau c divided by minus beta plus I alpha 0 to infinity plus e to the power minus beta minus I alpha tau c divided by minus beta minus I alpha 0 to infinity plus 1 by beta, which gives a into a minus 1 by 2 1 by beta plus I alpha plus 1 by beta minus I alpha plus 1 by beta, that is equal to a into a minus 1 by 2 beta divided by beta square plus alpha square plus 1 by beta, which further can be written as g omega is equal to a into capital A 1 by beta minus beta by beta square plus alpha square, that is equal to a into a beta square plus alpha square minus beta square divided by beta square plus alpha square into beta, which gives a into capital A alpha square divided by beta into beta square plus alpha square. Now substituting the values for a is equal to e naught square beta by 2 pi square. We get g omega is equal to a e naught square beta divided by 2 pi square alpha square into alpha square divided by beta into beta square plus alpha square, that is equal to a e naught square divided by 2 pi square beta square plus alpha square. So line shape function for the collision broadening, we get a e naught square divided by 2 pi square into 1 by 1 by tau naught square plus omega minus omega naught whole square, where a is the normalizing factor. Now we shall find this small a by using the condition of normalization of the g omega, that is 0 to infinity g omega d omega is equal to 1. So let's solve this. A e naught square by 2 pi square 0 to infinity tau naught square by 1 plus tau naught square into omega minus omega naught whole square d omega is equal to 1. Let's put omega minus omega naught tau naught is equal to u. So d omega is equal to d u by tau naught. Therefore a e naught square tau naught square divided by 2 pi square 0 to infinity 1 by 1 plus u square du by tau naught is equal to 1. Therefore, integrating this, we get e naught square tau naught square divided by 2 pi square inverse 0 to infinity is equal to 1. This implies that a e naught square tau naught by 2 pi square into pi by 2 is equal to 1. One tau naught is also there. So this implies that a is equal to 4 pi divided by e naught square tau naught. So we get the normalization constant a. Now after substituting this value of a, we get the final line shape function for the collision broadening, that is equal to 2 by pi tau naught 1 plus omega minus omega naught square tau naught square. So this is the normalized shape function. This is again a Lorentzian. So full width at half maximum will be given by 1 by 1 plus omega minus omega naught whole square tau naught square is equal to 1 by 2. That gives omega minus omega naught whole square tau naught square is equal to 1. That means delta omega plus minus is equal to 1 by tau naught. That is full width is equal to 2 by tau naught. Thus, this is the collision broadening. Thus, a mean collision time of 10 to the power minus 6 second corresponds to the frequency 2 pi into 0.3 megahertz, and the mean time between collisions depends on the mean free path and the average speed of the atoms in the gas, which in turn would depend on the pressure and temperature of the gas as well as the mass of the atom. An approximate expression for the average collision time is given by tau naught is equal to 1 by 8 pi 2 by 3 to the power 1 by 2 m k t to the power 1 by 2 divided by t a square, where m is the atomic mass, a is the radius of the atom, and p is the pressure of the gas. Assuming that a hard sphere in the case of the atom. So friends, in this video lecture we covered about the line broadening mechanism in the laser, and we did the detailed study about the homogeneous broadening, that is natural broadening and collision broadening, and we derived for each cases the line shape function, and we found the full width at half maximum for each of the cases like natural broadening and collision broadening. So friends, I hope that you enjoyed this video lecture and you learned about the broadening mechanism in detail. So if you like this and if this video helped you, please press the like button. And if you have not subscribed this Sai Academy channel, please subscribe this, because this action of you motivate us to provide you the best quality lecture on physics. And if you have any query, doubts regarding this lecture and any another topic of physics, please give your feedback and comments in the comment box, and please stay tuned throughout whole of the videos. Thank you.